Today we're talking about catalysts and reaction mechanisms. Sounds like fun, eh? Alright, so catalysts. Speed up a reaction without being consumed. That would just be the definition of them. Again, catalysts speed up reactions without being consumed. If you take an AP Bio, we have lots of catalysts in our bodies. They're super helpful for biological function. And we also use them in chemistry for this very thing, to speed up reactions. And next little bullet, A, is going to be their function. We've kind of already talked about these speed up reactions. Well, how do they do that? Well, their function is basically to provide a more efficient, so their function is to provide a more efficient, and really by efficient we mean there's less time and energy. So we can provide a more efficient, which means less time or energy, reaction pathway by decreasing the energy of activation. So in their primary function, provide a more efficient reaction pathway by decreasing the energy of activation. In a little bit I'll kind of have a graphic out of your book that kind of is a graphical display of that definition. And then the other thing we're going to talk about is there's basically two different types of catalysts. And these are pretty straightforward as far as definitions go. You might just jot these down real quick though. Homogeneous. And again, this has been drilled into you from other science classes, but homo means same. And really with geneous we're talking about phases. So all homogeneous is the same phase. And because reactions are really concerned about reactants, when we're talking about kinetics, they're the same phase as the reactants. And some examples, I think I mentioned this above, but examples would include anything that, or most of the things that happen within our bodies. And that would include solutions. So our blood is a solution. We have catalysts in our blood, but liquid, or maybe more specifically solution. So stuff dissolved in liquid, and primarily stuff dissolved in water. And it also might be acid-base stuff. This would be more applicable to chemistry, but acid-base chemistry, acids and bases can act as catalysts, and again they're liquid, or really better term, solution, homogeneous types. And then we also have heterogeneous, which obviously is different phase as reactants. And your book does a nice job of explaining this, but anything that's like on automobiles, we'll get this jotted down first. Heterogeneous, different phase, as reactants, we'll leave as reactants off. But a good example is cars. You've probably heard of catalytic converters. And they are part of the exhaust system. For those exhaust gases that come out of the actual engine, before they come out of your tailpipe, they go through really a set of catalytic converters. And the first of those really takes, these catalytic converters are gas solid, because you have gas coming out of your exhaust, and the catalytic converter itself is some sort of solid, usually with some sort of pretty expensive metals. But the first catalytic converter takes carbon monoxide, which is a dangerous gas, and just leftover hydrocarbons, so we're just going to call that CX some number, Y some number, and then any kind of oxygen. We have lots of ozone that is created in our engines, but it might be O2, it might be O3, which is ozone, and it basically converts these things hopefully into carbon dioxide and water. And then the second catalytic converter takes our nitrous oxides, or different nitrogen oxides, so nitrogen monoxide, nitrogen dioxide, and it converts it into just nitrogen gas and oxygen gas. So even though our cars are fairly polluting, without catalytic converters they would be even worse for the environment. So here is an example of a reaction that involves what we would call a catalyst, and also the term intermediate. Try to leave a little bit of room to the right with this reaction because we're going to come use it again a little bit later in the notes. But we have two hydrogen peroxides, and we're just going to write those as aqueous. In these reactions, phases are important. You'll see as you start doing examples, but phases are important. So two hydrogen peroxides that are aqueous yield two waters, which are liquids, and an oxygen, which is gas. All right, and this is already written as a balanced equation. And it's really, really slow. If you have bottles of hydrogen peroxide at home, if you were to leave the cap off, eventually that hydrogen peroxide would turn into water, and the whole time it's turning into water you're getting oxygen gas, but it's a really, really slow process. And it's why we have to replace hydrogen peroxide every so often, because it's just not as effective anymore, because it's being diluted down by it turning into water. So if we add iodine to this thing, it speeds up, and we can actually see oxygen bubbles being formed because it's reacting so quickly. So this process, as we add iodine, happens in two specific or separate steps, which we're going to call a little bit later elementary reactions. All right. So in our first reaction, we have hydrogen peroxide, and I should have written aqueous here. And after I tell you it's important, I leave it out. But hydrogen peroxide aqueous plus iodine is going to yield water as a liquid plus IO minus. And again, it is all balanced. We have two H's, we have two O's, we have an I, and there's a negative charge on the left and there's a negative charge on the right. Our second step, we are going to take some more H2O2 and react it with that IO negative that we created. And this reaction is going to yield water. It's also going to yield oxygen, and it's also going to yield I minus again, or just iodide ion. And what we see is we can add these two steps together to get an overall equation. Or I'm going to write here total equation. You'll kind of see it either way, but overall is probably more correct. So we really have two hydrogen peroxides, and then we're going to circle some stuff here that kind of cancels on both sides. We have an iodide on the left, and we also happen to have an iodide on the right. So we're not going to include it in our total. Just think of them in math, they cancel each other out. We also have this IO minus on the left, and we have an IO minus on the right. So we're going to not include them either because they cancel out as well. So we really go back to, we have two hydrogen peroxides, and that's our only reactant, and we have two waters, and we have an oxygen. Or not oxygen, but we have oxygen gas. So this reaction equals our total reaction above. Alright? So the things I circled, one of them is the catalyst, and the other one we're going to term the intermediate. So the catalyst, as far as definition goes, is anything that's consumed and produced. I'll write this in blue. It's going to match our I minus. So in the above example, I minus is the catalyst. And again, leave room on the right-hand side of our equations because we're going to add a little bit more a little bit later. So consumed and produced, and that is our I minus. The other thing we have is what's called the intermediate. And the intermediate, I'm going to go change my ink to green, is this thing in green. So it is something that is produced and consumed. And in this case it is the IO minus. So notice the iodide, we have it to begin with and we have it to end with. We use it in the middle, it's effective for us, it does something for us, but we start with it and we end with it. And notice the intermediate is something that we do not start with or end with, it's in the middle. Okay? And notice that neither are really included in the overall equation. If we look at our overall equation, we have hydrogen peroxide, we have water, we have oxygen gas, and we don't have iodide or the IO minus ion. Again, they are only in our elementary steps, but not in the overall. Alright, the next thing we're going to look at is our energy profile, or our energy diagram. And it's what we looked at a couple days ago. So, if we look at energy diagrams for this and go back to our first definition that said that catalysts provide a more efficient reaction pathway by decreasing activation energy, this is out of your book, and it is figure 1317. And the left picture is an uncatalyzed energy diagram, while the right picture is a catalyzed energy diagram. Notice in both equations we're going from A plus B, and we're forming C plus D. The activation energy on the left one is quite high, that on the right is quite low. Kind of pictorially, we can just think of something being catalyzed as you have a really tall mountain you have to go across. Well, it takes a lot of energy in your car to do that. Alright? Well, if we can decrease the activation energy, how do we do that in a mountain? Well, we drill a tunnel. Okay? It takes less energy for your car to get through, but you still go from the one side of the tunnel to the other side of the tunnel. So you still get through the mountain, but instead of going over the top, you go through the middle. Alright, Roman numeral 2. It's been a long unit, and we only have 2 Roman numerals, but Roman numeral 2 is reaction mechanisms. And we actually just saw one of these. It was in our example above where we kind of broke stuff up into steps. Well, reaction mechanisms are a series of steps that produce a net reaction. So a series of steps that produce a net reaction. And your book does a nice job in figure 1320 kind of showing this. So we measure the rate of the reaction experimentally. From that data, that experimental data, we can kind of formulate the rate law. If we see something, if we double something, what happens to the rate? Does it double? Does it quadruple? Does it increase 8 times? What happens to it? And then from this data and our equation, we can begin postulating possible mechanisms. Okay? So more data and really a little bit of guesswork. So more data, and it's always a guess as to what's really happening. We can never be completely sure because we really don't see reactions happening at the molecular level. We know the results of those reactions, but actually seeing molecules react with each other, we don't have the technology to see that. Alright, so kind of a mechanism of where we're going. We've kind of talked about those first 2 things, and now reaction mechanisms is what we are headed towards. So if we go back to our reaction up here that we looked at earlier, hydrogen peroxide yields water and oxygen. We can always define one of our steps as a slow step, and another of our steps as the fast step. And these, again, are determined experimentally, but one of them is what's slow and one's fast. If we look at energy diagrams, they usually give a good indication as to which is the slow and which is the fast step, because the slow step typically has the higher activation energy. Once it gives over that major hump, it can go over smaller mountains after it. Okay? So the slow step is always what's known as, well, I'm skipping ahead. So let's rate the rates of our steps. So our rate for our slow step is rate equals K times hydrogen peroxide. That's one of our reactants, and it's also times iodide. And our fast step is going to be rate times, or rate equals K times the concentration of hydrogen peroxide times the concentration of IO minus. Alright, and we can kind of go down here and do a little bit more work. We're going to go back to our notes, and our reaction mechanisms are always made up of elementary reactions. And again, these are equivalent to our steps. Any step is an elementary reaction. And they're kind of just defined as singular molecular events. So again, elementary reactions or steps, defined as single molecular events. So here's an example of one. We have A, which is our reactant. It yields products. And if we were to name this, how many reactants do we have? We only have one. So it's a unimolecular event. There's only one molecule we're concerned about. And if we write the rate law for this, we're going to write rate equals K times the concentration of A. Alright, another example. We might have A plus another A yield some sort of products. And again, products we don't care about because our rates are only concerned with reactants. This would be a bimolecular event. How come? Because we have two molecules that are reacting. And our rate law would look similar. It would be rate equals K times concentration of A times concentration of A. Or we might say K times A to the second power. Again, this is going to look really similar. We have A plus B yields products. How many molecules do we have? We have two of them, so again it's bimolecular. And our rate law, because we have differing reactants, is going to look a little bit different. But it's going to be K times concentration of A times concentration of B. And then we can also have trimolecular events. I'll let you guess what that means. Well, we have three molecules. So we have A, we have another A, we have another A, and it yields some sort of product. And our rate's going to look the same. We have rate equals K times concentration of A, times concentration of A, times concentration of A, or A cubed. Trimolecular events really, for all intents and purposes, are very difficult and do not necessarily happen all that much because of orientations. Again, we talked about things have to be oriented. They have to have sufficient energy, they have to hit each other, and they have to be oriented correctly. And it's very unlikely that three things will hit each other on just the right sides at just the right speed. So these are very unlikely. So really, our most likely are our bimolecular events. And that is what we have listed above from our equations. And notice these, our orders match our coefficients. Okay, so how many A's do we have? We have one A. On our second example, we have really KA2. And how is A plus A really written? It's usually written as 2A. So again, our order of 2 matches our coefficient of 2. And again, if we go to our next one, A and B, they both have first order. And what are the coefficients in front of A and B? They are both 1. So 1A plus 1B yields products. So when we're talking about elementary reactions, order equals coefficient. Right? And again, K, A cubed, really is 3A. But again, from this, during elementary reactions, and this is key, this is not rate law, but elementary reaction, order equals coefficient. Alright, so if we go back up to our example above, scroll, there we go. Alright, so we have two different rates. We have our slow rate law and we have our fast rate law. Well, our rate law for our reaction is always dependent on our slow rate. Okay? So our slow reaction, or our slow step, always determines our overall rate law. And our slow rate law was K equals hydrogen peroxide, concentration of hydrogen peroxide, times concentration of iodine. And notice from our step, we have coefficients of 1 for both of those. So they both have orders of 1. Good. Slow step. Slow step equals rate law, or determines our rate law for our overall equation. And again, because it has the slower rate, whatever rate it is must be the rate of the reaction, therefore it determines the rate of the reaction. As soon as that IO is formed, it reacts immediately with hydrogen peroxides that are still in solution to make water, oxygen, and iodide back. We're going to do one more example, just so you have a couple of these, and that is it. Again, once we're done, here's a great graphic from your book as well. So here is kind of a two-step potential energy diagram. That first step you can see is the slow step. It has a higher activation energy. And really, I kind of imagine you're at a bicycle at the top of a hill. You don't need a pedal, and could you make it down that first peak and go over the second peak? Sure, because you have so much energy coming down the hill, you'll get back up the next activation energy. Alright, so our slow step is the left one, because the activation energy is higher. Fast step's the second one. If our slow step happened to be the second one, just our activation energy would be higher on that second hump. And then our intermediate is that thing in the middle. So in our case above, it was the IO minus. Alright, so one more example, here we go. And in this equation, we are going to have, for our step 1, so I can get the color straightened out. Nope, okay, we'll just stay orange then. So step 1, we have NO2 plus NO2. How could we write that? We could just write it 2 NO2s, but we're going to keep it separate. A bimolecular event. And these things yield NO and NO3. And our second step, NO3 plus CO yields NO plus, or I'm sorry, NO2 plus CO2. And that's step 2. Alright, so if we look at our overall equation, let's again see if we can identify catalyst and intermediate, or things that are the same on both sides, because they are going to be the things that are canceling out. So we have an NO2 on the left, and we've got an NO2 on the right. We have an NO3 on the right, and we have an NO3 on the left. Alright, so in your summary, please identify the catalyst. Is the catalyst NO2 or is it NO3? Alright, so if we write what's left, we have NO2 plus CO, or nitrogen dioxide plus carbon monoxide yields nitrogen monoxide plus carbon dioxide. Alright, in a book or homework or AP test, you're going to be given what's the slow reaction and the fast reaction. So our slow one happens to be our first one again. Our fast happens to be the second. This is not always the case. It just happened on both our examples that slow is the first. So our rate law for our first one is really K equals NO2 squared. And our rate for the second one is, I'm sorry, these are written bad, rate equals K times NO2 to the second, and rate equals K NO3 times CO. Right? And because our slow determines our rate is really, and I butchered this with my writing, rate equals K times NO2 to the second. So second order reaction, and again, if you can identify the intermediate for me in your summary, that would be awesome. Thank you.